Swayam Prabha. Digital India. Educated India.
Welcome to Module B, Lecture 4. In this lecture, we shall discuss about single regime traffic stream models. In Lecture 3, I mentioned to you about the macroscopic density parameter, that is how to quantify, what are the difficulties, and if we want to estimate using occupancy, then how we can estimate it. Then explained you the relationships between the speed, density and the flow. Among all these parameters, also the separate relationships between speed and flow, speed and density and flow and density, and then highlighted the importance of field location, where you are collecting the data and under which condition at what time. That will determine that what data you will get, what curve you will fit and how that will match closely with the, or how that will match either closely or remotely with the theoretical curves. Then also indicated how the speed flow curves look like for a modern freeway. With this background, today we shall entirely focus on single regime models. Why we call it single regime? Several analysts attempted to fit relationship to observed data. As I said, they collect the field data and try to fit the relationship, the speed density relationship and also other relationships. Considering single regime phenomenon over the complete range of flow condition. One relationship explaining the behavior, say how density varies with flow or how density varies with speed or how speed varies with density, not flow, how speed varies with density. That relationship is explained, entire range is explained using a single expression, a single equation. That is what I said, that a single regime phenomenon over the complete range of flow condition. Obviously, this will include both stable flow and forced flow condition. Here for example, you can see these green segments, it indicate the stable flow condition, capacity is somewhere here, and this red line indicates the congested or forced flow condition. But a single equation, a single regime phenomenon over the complete range of flow condition. That is what we say, that this is a model which is a single regime model. There are three major models that we are going to discuss in today's class. One is Greenschild's model, then Greenberg's model and Underwood's model. These are the three models we shall discuss now. First, coming to the Greenschild's model. Greenschild's model assume linear relationship between speed and density, the simplest one, but I will also say a very practical one, simple one, but a very practical and very meaningful one as well. So, the relationship can be explained using this equation as shown here. V s equal to V f, V f is the free flow speed minus V f by k j, Kj is the jam density, Vf is the free flow speed multiplied by k. So, this shows how the k changes and correspondingly Vs. So, speed of traffic stream, how it changes. Now, there are certain boundary conditions which are to be satisfied. If Vs equal to Vf, that means I am talking about the free flow condition, then what you will get? You will get k equal to 0, that is what you get here. And therefore, if you substitute, put Vs equal to 0, k equal to then Kj, that will be there. So, this is the free flow condition when Vs equal to Vf, free flow condition, then density is 0, and when Vs equal to 0, standstill condition, that means the density is equal to the jam density. At Q max, let us consider when the capacity flow occurs, then let us consider Vs is equal to Vm, and at capacity flow k is equal to Km. Now, how if this is the linear speed density relationship, then what will be the corresponding flow density and speed flow relationship? These two relationships will look like parabola. How we can get that? We can get it putting Vs equal to q by k in equation 1. That means, whatever equation we have shown here, Vs equal to Vf minus Vf by Kj into k. In this equation, we are substituting Vs using q and k. So, this whole equation now becomes relationship between q and k. You can see this equation and you can see that it is going to take a shape of a parabola. Similarly, if you replace k with q by Vs, that substitution if we do in equation 1 instead of this substitution, that means I am replacing Vs here, but I am bringing k. So, now the relationship will be if we replace Vs equal to q by k in equation 1, and then in another case if we replace k equal to q by Vs in equation 1, then we shall get these two equations. Both are actually parabolic equation. This shows the relation between q and V, and this shows the relation between q and k. So, both cases you will get equations which are parabola. At low density, flow appears to be 0 and speed approaches free flow speed, as I have explained. So, if you take a point when the density is very low, then the flow also becomes 0 and speed approaches to the free flow speed here. And as flow increases, density also increases, we are increasing the flow. So, density is also increasing, and as the flow is increasing, the speed is decreasing, and at maximum flow condition, optimal density and optimal speed is achieved. How to get that? We can differentiate equation 2 with respect to k. So, here we can calculate dq dk. make it equal to 0, and another derivative we can take, we can equation 3 we can take and differentiate this with respect to V s. That is what this equation. So, if you do that, what we will get? You will get here dq dk equal to V f minus 2 V f into k by k j, and that indicates that when dq dk equal to 0, if when it will be 0, it will be at speed when the capacity flow has reached. So, at capacity the density K m is equal to K j by 2. Similarly, if you take this dq dv, it is equal to K j minus 2 K j into V by V f, make it 0, and we get speed at capacity is equal to V f by 2. So, if these two are fine, that means, if the speed density relationship follows the Green-Schild model as shown in equation 1, then at capacity as per that the density will be half of the jam density and speed will be half of the free flow speed. So, then what is actually the q m? Q m capacity value would be V m into K m. So, V m is V f by 2 and K m is K j by 2. So, you get V f into K j by 4. Now, again this is valid if my assumption about the linear relationship of speed and density is valid as shown in equation 1. So, this is very simple, but very useful, but although Green-Schild's model used extensively in transportation analysis because of its simple form, you can see anything linear is always very simple to use, but field observations do not fully support the shape of the model. Some cases people got little better match, but some cases it did not give that much good match. So, further development happens, but before we go that or before we discuss that, let us take an example problem. Speed and density are related as V equal to 100 minus 0.5 k. Clearly, this is a linear equation as proposed by Green-Schild. So, it is a Green-Schild model. V equal to in kmph, k in vehicles per kilometer. Calculate the maximum flow on the stretch, capacity flow. How we do? We can, for maximum flow, we know that dq dk equal to 0 and we know q equal to kv. So, you take this q equal to k into v. So, 100 k minus 0.5 k square. Now, we take dq dk and we find k j equal to 100 vehicle per hour. That is the jam density. Now, V f will be how much then? 100 minus 0.5 into 100. So, 50 kilometer per hour. Use this equation directly. The k is known, so V is known. And once I know that and then this is not V f, rather it is V at optimal value, and this is k also is at optimal flow. It is not k j, it will be k m. This is also not V f, this should be V m. So, density at capacity is 100 vehicle per kilometer and speed at capacity is 50 kilometer per hour. So, what we get? The capacity value will be 50 into 100. So, it is 5000 vehicle per hour. Let us take another example. Space mean speed and density are linearly related. The moment we say speed and density are linearly related, that means I am saying it is a Green-Schild model. Vf equal to 80 kilometer per hour, kg equal to 100 vehicle per kilometer, that is the jam density, and we want to determine the capacity. So, according to Green-Schild's model, we know Vs equal to Vf minus k by kj into Vf, and also we know q equal to kv. So, take the q, k multiplied by this equation. So, k Vf into Vf into k square by kj. So, you put the value here, we know that kj is 100 vehicle per kilometer and Vf equal to 80. So, you put these values and we get this equation. Now, for maximum flow, because we say at capacity, so dq dk will be 0. So, put that, we get what is the value of k at capacity. So, that is the km, and similarly we get what is the speed at capacity, that also you can get, and then you can find out then km into Vm equal to the Qm. Now, as I said that although Green-Schild's model is very simple and quite a popular model among transport professionals or traffic engineers, and very simple one, very practical one, but not that always it will give you a good fit. So, people tried, researchers tried different alternatives. And now, I am going to show you a model which was suggested by Greenberg, and it is also another very well known model called Greenberg's model. And observing the demerit of Green-Schild's model, Greenberg suggested nonlinear, rather a logarithmic relationship between speed and density. What was suggested is like this, shown as equation 4 in the slide. Vs equal to Vm, remember that it is not Vf, not the free flow speed, it is the speed at maximum flow or capacity flow, you can also call it as optimal speed, into ln kj by k. So, this is a nonlinear relationship, but what you find, the model breaks down at low concentration. If you put k equal to 0, speed is infinity, any value it can take, right. So, therefore, this model normally is not used for low density region. This model is normally not used for the low density region, but it is used predominantly for a range where the density is moderate to high, because here otherwise it will give you a free flow speed which will be unrealistic. But does it really, is there any basis for that, why it is considering infinity or so much high value of speed? I will discuss it further. Let me complete the other model also, and then I will make a comparison. We can derive this Greenberg model from a generalized equation. Generalized form could be Vs equal to A into ln b by k. This is a logarithmic relationship, but we know that there is a boundary condition when k equal to kj, density is the jam density, then the speed is 0, Vs equal to 0. If you put that, you will get here b equal to actually kj. So, using this boundary condition k equal to kj, then Vs equal to 0. So, you can find out then b equal to kj. Now, what is then the Q? Q equal to V s into K, Q equal to speed into density. So, A k ln B by K. Now, for maximum flow, we can take the derivative dq dk, make it 0, and you get then dq dk as like this, as shown here, minus a plus a ln kj by km, that is equal to 0. Now, km equal to kj by E, and therefore, Vm you can write it as a ln E, which is equal to A. So, the Vm actually is the value of A. So, what is the value of A? It is actually Vm. So, now if you put it back to this equation, this will then become A becomes Vm and B becomes Kj. So, the equation becomes Vs equal to Vm ln Kj by K. Let us take a small example. The flow speed relationship is given by Q equal to 265 V minus 79 V into ln V. Now, this is a logarithmic relationship, and we can understand that it has actually come from the Greenberg's model, Greenberg's logarithmic model. Now, this includes this term. Now, you can see here, now the speed flow relationship includes the term you can see here that the speed flow relationship includes the term ln V. So, you can understand it has come from the logarithmic relationship as suggested by Greenberg for or between speed and density. But here we are giving it flow equal to this expression. So, now we want to calculate maximum flow. How we can calculate maximum flow? Take this and differentiate with respect to V. So, you can get dq dV, and from here you can find out what is the Vm. Once you know the Vm or V value at capacity, you can get the Q max value, put it simply in this equation, and once you know the Q max capacity value and speed at capacity, you can also get the value of Km. Simply it is Q by K, Q by V. So, that way you can calculate that Km equal to 79 vehicle per kilometer, speed at capacity Vm equal to 10.53 kilometer per hour, and Q max will give you 832 vehicle per hour. Now, Underwood also suggested another nonlinear model, because Greenshield suggested linear relationship. Contrary to that, Underwood also suggested nonlinear relationship, which looks like this: Vs equal to Vf into e to the power k by km. Remember that, note it carefully, that here we are not using kj, but we are using km, but V is Vf. So, speed is we are using free flow speed, but the density, it is not the jam density, it is density at optimal speed or capacity. Why this was suggested? Because primarily the Greenberg's model fails at low concentration. So, this is a model which does not fail at low concentration. So, could be utilized effectively. but then at the other end it fails, because it does not represent 0 speed at high concentration. You can see here, you can see from equation also, whatever may be the k value, the speed is unlikely to be exactly 0. It will still have a very low value, not 0. So, it does not represent 0 speed at high concentration. Let us take an example problem. The relationship between speed and density for a traffic stream on a road is given by this. You can clearly see that the relationship between speed and density is given by this equation. Calculate density at maximum flow, capacity of road and free flow speed of the stream. 3 parameters we need to calculate. So, take the equation V equal to 60 e to the power minus 0.1 k, and you can take then q equal to V into k. So, 60 k into e to the power 0.01 k, and at maximum flow condition dq dk equal to 0. So, you can take the derivative, make it equal to 0, and you can get here what is the value of k at maximum flow condition. So, that k is actually k. Once the density at maximum flow or capacity is known, you can actually calculate this q max, because we know 60 k. So, 60 into k is 100 into e to the power 0.01, and what is the k? K value is 100. So, you can get the q max. So, now you know V s equal to V f into e to the power minus k by k m. So, you put it here and it clearly tells you that what is the value of V f. V f is actually 60 kilometer per hour. Now, let us come to the applications part of it. There are 3 models: Greenschild's, very simple linear relationship, then Greenberg's, and then Underwood's model. Let us go one by one. As I said already that Greenschild model is very simple, but very practical. Why I said that? If you look at the Greenberg's model, let me go back there also, you can say it actually breaks down at low concentration. So, if I try to plot all the 3 model using a single plot, then this Greenschild's, the blue line is touching both x and y axis, that is both k and v, it is touching clearly. But then the Greenberg's model is touching this end, but not touching the speed axis. The speed axis it is not touching, density axis it is touching, as you have seen earlier that it is not touching the speed axis, Greenberg's model. So, here also Greenberg model is shown that it is not touching. What is the actual implications? Now, theoretically this may be all right as well. I consider this could be all right. Why? If there is no vehicle around, hardly any vehicle around, then why the density should influence your speed? What we are trying to capture here, trying to state here, how density influence the speed. If there is no vehicle around, then there is practically why there should be a loss in the freedom of movement. There is no loss. So, theoretically a vehicle can travel at any speed as far as the density is concerned. Density is not a factor. Any speed could be possible theoretically. So, I feel that Greenberg's this discontinuity here, what it said, it breaks down, is theoretically not wrong. What happens? Real data will show you like this? No. But that reason is different. When you design a road, you will have a design speed, you will have maximum speed limit as well. So, a vehicle can no way exceed those speed limits. So, the constraint whatever is coming, it is because of the road design. The constraint will also come because of the vehicle technology. A vehicle is not an Airbus. See, it cannot travel at any speed it wants. There are limitations with the technology. Limitations with technology, other considerations of safety, road design, all these factors will actually make even the free flow speed a particular value only for a given condition or a given context. But understand that restriction is not because of a density value. So, theoretically it might be all right to say that there is a discontinuity at the low density level, but because of the vehicle technology limitations, safety consideration, road design considerations and any other considerations other than the density, there will be a defined or a definite value of the free flow speed. Let us consider the other end now, Underwood model. So, the red line is shown as Underwood model, it is touching the speed axis, but it is not touching the density axis. It is again saying that density will never be, the speed will never be 0. Is this also very unrealistic theoretically? Again I feel no, it is not unrealistic. Why? Because yes, the freedom of movement will come down as there are more and more vehicles around, but why the vehicle should come to a standstill with a 0 speed? Why the 0 speed should come theoretically? If there are more vehicles, if just consider you are driving in a very lean period, no vehicle is around and then there are a few vehicles and the number of vehicle is more and more, it will affect your speed. But why? Because of more vehicle the speed will come down to 0 specifically. It should not come. Still there should be, vehicles should move. Why the speed should come to 0? Even if you consider the congested operation, 0 speed average, how that is possible? So, I also feel that theoretically it might be that it will not touch this x axis, it is coming down, it is not telling exactly 0. In reality, it will come so low that you can consider that it is touching. Beyond certain density value, which you can consider as jam density, you can consider the speed is practically 0. That could be a very realistic assumption as well, that to assume that then density could be up to a maximum value. That approximation is fine. So, altogether each of these models, 3 models, Greenshield, Greenberg and Underwood's model, each of this model has its own merits as well and considerations. The fact remains true, what is common in all the models, that as density starts building up, there will be loss in the freedom of movement and therefore, the speed will come down. How exactly speed will come down, whether it will follow a relationship as given by Greenshield, exactly linear, may not follow. It may not follow even Greenberg's model, it may not follow in Underwood's model as well, because the way the density will influence the speed will also depend on the many other conditions. I have remember my previous lecture, where you are collecting the data, on which road, what you can get in an arterial you will not get for a freeway, at what location you are calculating or recording the data. So many things, so many considerations will be there. What nature, how it will get reduced, following Greenshield's curve, following Greenberg's curve or Underwood's curve or any other curve, that is a different issue. It will vary depending on prevailing roadway, traffic and control conditions, and maybe many other factors, where you are doing what, when you are measuring, what is the observed thing. Accordingly, we will get the data and try to fit a curve. And this discontinuity at very low density and also discontinuity at very high density, they also, the theoretical part and the practical considerations, that connection is very interesting. Now, as I have shown here, the speed density curve for this three models, Greenshield, Greenberg and Underwood. I have shown here also the corresponding speed flow curve and flow density curve. As you can see here, the Greenberg's model give infinity, it does not touch the free flow point, right, on speed axis. So, here also Greenberg, it does not touch, it looks like this. And how the flow density will look like, here also the red one, Underwood model, will not touch the density axis. So, that is what is shown here as the red line. Now, when you want to calibrate single regime model, that is very important, we need to calibrate with the field data. So, traffic data were used to determine stream characteristics. We try to find out what is the jam density, what is the speed and density at maximum flow and such meaningful measurements. Usually involves collecting appropriate data and fitting the data points to suitable model. And in almost all the cases, we use linear regression model. Generalized form is something like y equal to a plus b x, y is the dependent variable and x is the independent variable, and a and b are the coefficient estimates, which we obtain for a given data, how best these coefficients are estimated using the least square techniques. You know, the sum of the squares of errors that we are trying to minimize through the fit. So, when we are accepting a model, generally what are the properties that we should check carefully? We should look at obviously the R square value, the coefficient of determination, higher R square is the better, obviously better fit, but we also look at the values on A and B, what value we are getting actually, right, because there is a physical meaning of that. So, that has to be realistic. Even the sign, everything we should check, right, before accepting this, and also we should check the statistical significance of the coefficient estimate. You get some value of A and B, but are these estimates statistically significantly different from 0? That also you need to check. It is significant, but statistically significant or not. That also that we should check. Now, there is an example problem here. The k and u values are given, simple one. None of you will probably actually calculate it using your calculator. You will use Microsoft Excel or any other platform to readily fit the data with a model, fit a model for the given data, readily fit a model for the given data and calculate the value of A and B. But here I have shown the equations and the calculations also. So, if you want to do it on your own for better understanding, you can do it. You can match also the calculation, how we can calculate A and B, and then each calculation is shown here. Now, another example I have given, determine the best fitted model using the following speed density data. So, I have given the speed data, I have also given the density data, and I am trying to fit Green-Schiltz model, Greenberg model and Underwood's model, all the 3 models to this given data. Again using regression equation only. I have not shown here each and every step. You can simply try to generate what is the best model that you get out of the given data. If you consider Green-Schiltz model, if you consider Greenberg's model and if you consider the Underwood's model, right. You can use any computer software, maybe Microsoft Excel to do that. Please do it and check it. I have given you the equation here, Green-Schiltz model A, Greenberg's model B, Underwood's model C for the given data, how they are fitting, the equations are giving here, and you can see here for this case, for the given data, the best fit is actually the Green-Schiltz model in terms of the highest R square value. So, we take that because of this. And you can accordingly calculate what is the jam density and what is the maximum flow. Jam density you can calculate and also you can get the maximum flow, that is 1845 vehicle per hour. So, altogether what I discussed here is the single regime models, 3 particular models, Green-Schiltz, Greenberg's and Underwood's model. Green-Schiltz assume linear relationship, Greenberg's assume logarithmic relationship and Underwood's speed density model assumes exponential relationships. I have tried to explain you how we can compare these models and how we can calibrate these single regime models from a given data using least square method or using linear regression technique to estimate the coefficients that best fit the given data, best fit the model for the given data and how to select the best model. With this I close. Thank you so much.